All right, let's start looking at the rational function. Rational function is a fancy way of saying fractions.
No.
Or should I say rational is a fancy way of saying fractions. Where our rational function is 1 over x. Important to note that our variable x is in the denominator, because strange things can happen when that occurs. Our graph kind of looks like maybe a half star or something. It's kind of bends. There's two halves to it, separated by the x and y axis. We'll talk about why that happens when we look at the attributes of rational functions. We saw this last year when we talked about the domain and range of rational functions, and those are affected by the asymptotes. So a rational function will have a vertical asymptote, could have more than one. There actually is an infinite number of possible vertical asymptotes it could have, and it may or may not have horizontal asymptotes, but those are also a possibility. So the reason why our graph looks the way it does is because when our graph approaches one of these asymptotes, it doesn't really want to touch it. It's kind of bending away from it. Maybe you could call it the Cootie line. Maybe, like Junior, you can call it the MC Hammer line. Can't touch this. Because with vertical asymptotes, your graph will never, ever touch that line. It's going to get really, really close, but it's never going to touch. That can't be said for horizontal asymptotes, but it is kind of trending along that line, and kind of maybe looks like it won't touch. Sometimes it will, sometimes it won't. So we have to deal with asymptotes, and they affect, like I said, the domain and range of rational functions. Where our domain, it would be all real numbers going from negative infinity to positive infinity, except for the fact that we have that vertical asymptote there. And as I mentioned, the graph will never equal or touch that asymptote. So it's going to bend away, and I could say the domain is all real numbers except for my VA, my vertical asymptote. Where the range is kind of the same thing. I could go all the way up to infinity and all the way down to negative infinity. And my range is going to be all real numbers except for where it curves and does not want to touch the horizontal asymptote. So all real except for HA. Sometimes. Or should I say, as far as this class, we'll just assume this is true, even though this is not. Sometimes it can be all real numbers because sometimes it can cross a horizontal asymptote, and sometimes we won't have a horizontal asymptote. But we'll just assume for the most part that this is true. Which makes how to find asymptotes really important. So let's look and see how we can find our vertical and horizontal asymptotes. First, vertical. As I look at my function 1 over x, I note that my variable is in the denominator. If you were to plug in 0 for x, you get 1 over 0, and that's a big no-no. You cannot divide by 0. Try to do this in the calculator, it'll tell you error. Or say, whatever it says. They all say something different. Because I cannot divide something out of nothing. If you ask me, hey, can I borrow a pencil? I can't give it to you if I don't have it, right? That's where you get that error. And this is when we get our vertical asymptotes. So whatever value for x will make the denominator 0, that's the value that will give you your vertical asymptotes. So we'll start simple. A rational function that's already been factored here with our terms. I have 1 over x plus 2 times x minus 3. Before I think about anything, I want to decide what values for x when I plug in will make the bottom 0. So this term here, x plus 2, what plus 2 will make that 0? A negative 2. This one here, x minus 3. What minus 3 will make that 0? 3. So I know my values for x. They cannot be negative 2 and 3. When I get those values, my calculator is going to crash. Likewise with the graph. The graph is not going to like those values. So when you're talking about vertical asymptotes, it's going to equal negative 2 and 3. has to kind of be written in this format, x equals, because an asymptote is a line. You can't just call it a point. It's not trying to say from this point. It's trying to say from all of these points here. It's kind of saying, nope, let me see if I can get over those points. It never will, because that line goes to infinity. So looking at this graph, I do see that there's a point at 3 that my graph turns away from. And there's a point at -2 that my graph turns away from there. So x equals -2 and x equals 3 are my two vertical asymptotes. What makes the bottom 0? I mentioned these are already factored. There's a reason why we spent time factoring last year, and that is because, well, they kind of pop up here too in this section. So if x squared minus 9, I want to look for the vertical asymptotes, so I'm looking for what makes the bottom 0. Kind of helps if you have it factored.
3 positive.
So how does it factor? X and x. This happens to be a perfect square, so what is it?
3 and -3.
Yeah, x plus 3 and x minus 3. A little bit easier to see what makes that denominator 0. So what values for x will make this term 0? What plus 3? Minus 3. What minus 3 is 0?
3 plus 3.
Plus 3. So my vertical asymptotes will be at what? X equals -3 and x equals positive 3. And if I were to graph it, so let's say you're not really strong, you're still not strong in factoring, you can always graph and see what line, invisible line, is your graph curving away from, like so. From here I can see it's at 3 and -3. So that's how you find vertical asymptotes. You make the decision, what will make the bottom, my denominator, 0. All of those values will equal vertical asymptotes. Horizontal is a little bit different. Horizontal asymptotes comes with a table of rules. Table of rules you don't have to memorize because you'll be given these on the test. First thing you need to do is to look at your numerator and find out what is the highest power. I'm going to call that x to the n. So my highest power here is n. Then you need to look at the denominator and find the highest power there. I'm going to call that highest power of the denominator d. So I'm looking at my table here. If n is greater than d, so if the highest power in this whole rational function sits in the numerator, then you will not have a horizontal asymptote. So if your numerator has the highest power, you won't have any horizontal asymptotes. Flip that. If n is less than d, if the denominator has the highest exponent, then your horizontal asymptote is y equals 0. That will always be the case. So maybe you can think of a little cheat sheet here. If the numerator is higher, that would be a no. If the denominator is higher, that would be a y equals 0. No if on top's the highest, y equals 0 if the bottom's the highest. There is another case to where what if the numbers are equal? So if the highest power in my numerator is the same as the highest power in my denominator, then I need to look at the coefficients in front of those. So I'm looking at the number in front of my highest power, A. Looking at the number in front of my highest power in the denominator, B. The horizontal asymptote will equal A over B. So you're just grabbing those from the top. That becomes your horizontal asymptote. So basically if they're equal, then they cancel each other out, and you're left with A and B. Some examples. X cubed plus x minus 1 over x squared minus 2x. Highest power in my numerator is a 3. Highest power in the denominator is a 2. Looks like the numerator wins, right? It has my highest power, and that means, referring to the table, no horizontal asymptote. By looking at the graph, it doesn't look like there's any graph that kind of turns towards a visible horizontal line, like so. I don't see any of that going on. I see some verticals. I see what we're going to look at next week after the test, a slant asymptote, but I don't see anything horizontal. That's because my numerator had the highest power. Next, x squared minus 2 over x to the 4th power plus 3x. Highest power in the numerator is 2. Highest power in the denominator is 4. 4 is the winner. It's the highest power. So since the denominator had the highest power, then y equals 0 is your horizontal. If you were to graph it, you would see that my graph kind of turns at y equals 0. Now notice I did mention horizontals do kind of cross. But this will bend back towards the graph. Start kind of riding along it again. Vertical asymptotes, your graph will never cross. And then last but not least, I have 3x cubed minus x over 2x cubed plus 2. Highest power with both the numerator and the denominator is a 3. They are equal. They pretty much cancel each other out. So what decides my horizontal asymptote? Well, that's the coefficients. And I see 3 over 2. So my HA is y equals 3 over 2. That's how we identify horizontal asymptotes. Via the table. I've written all this here so you can reference. Go ahead and practice while I take my attendance. This first 3 here on the left side, only find the vertical asymptotes. The 3 on the right side, find the horizontal asymptotes. 1 over x plus 1 times x minus 2. First off, is the vertical asymptote an x equals or a y equals? What kind of line is it? X equals, because it affects the domain, and domain is talking about the x. All right, so x equals, what values will make the denominator 0?
-1 and 2.
Very good, -1 and 2. Basically flipping the signs of those. Number 2, might have to do a little factoring. X squared plus 3x. What did I say twice?
X squared plus 3x.
What did you just say twice?
X squared plus, hold up. X squared plus 3x.
What word did you say twice?
X squared.
X, yeah, great. So, they both have an x in common. So I'm going to take out an x. I'm going to take 1 away from 2, gives me 1 left over. If I take this x away from 3x, I'm just left with a 3. So it factors into x times x plus 3, making it a little bit easier to see my zeros. Therefore, my vertical asymptotes are x equals what? What number do I plug in for x to make that 0?
1.
What number do you plug in to make it 0?
Wait. I'm trying to think what number. I said 1, but it's not 1.
You want this to equal 0. So what do you plug in?
0.
0! Very good.
Oh.
There we go. Yep, that is 0.
It's 0.
Now, what do I plug in to make x plus 3 0? A -3. There's your asymptotes. Number 3, 3 over x squared minus 16. I gotta factor that x squared minus 16. And can somebody tell me how does it factor?
Like 4 and plus 4 minus 4.
X plus 4 times x minus 4. Yep, that's a perfect square that follows that a plus b, a minus b. In this format, I can easily see what my vertical asymptotes are going to be, and they're going to be at what values? X equals? -4 and +4. Not so bad, right?
Super.
We've kind of been doing this a lot. Finding zeros. You're probably getting tired of it by now. Well, that's what you need to do with the denominator. Find your zeros. So I guess technically you could graph all the denominators here and look for x-intercepts. That'll give you the same response. Now we will look at the horizontal asymptotes. So x4 plus 3 over x squared minus x minus 3. What's the highest power of my numerator?
4.
4. What's the highest power of my denominator?
2.
2. So who had the highest exponent? Numerator, which means what's my solution?
No horizontal.
Very good. If the numerator has the highest, then you have no, what am I trying to say here? No horizontal asymptotes. Number 2. What's my highest power in the numerator?
3.
What's the highest power in the denominator?
3.
Ooh, they're equal. So now that they're equal, what should I look for? They're equal. So they cancel each other out. So what am I looking at next? What? The next highest, not the next highest. Let's go look at that formula again. They're equal. You then want to focus on the coefficients in front of them.
Oh, the highest, that's the highest equal to the denominator.
So, what's my coefficient in front of x cubed? 3. What's the coefficient in front of this x cubed? 1. So therefore, my horizontal asymptote is that x equals 3. 3 over 1 is 3. Last but not least, my highest power in my numerator for number 3 is a 1. Highest power in the denominator is a, so the denominator had the highest exponent, which means my horizontal asymptote is y equals what? When the denominator is greater, y equals 0. Yep.
Oh my god.
Y equals 0. The numerator is greater, no horizontal. The denominator is greater, y equals 0. If they're equal, take the coefficients. That's how you're going to find your horizontal asymptotes. Now there is one thing that occurs. Rational functions do have one other unique attribute, and that is a hole. There is a possibility that you could have a hole in your graph. And it's literally what it means. I have a spot in my graph where this x value has no y value, or that y value is undefined. It works the way like this. I have x minus 2 over x minus 2 times x plus 1. You can simplify this, can't you?
Yeah.
What crosses out?
The x minus 2.
The x minus 2's, right? That's going to give me a new rational function of, make sure it's red, 1 over x plus 1. Or sorry, x plus 1. X plus 1. Which means I'm going to have a horizontal asymptote, a vertical asymptote at what? X equals minus 1. That's my vertical asymptote. So here we can see vertical asymptotes will show up no matter what when you have the rational function simplified. Problem comes with holes. Holes will never show up in a simplified rational, meaning a simplified rational will never have a hole. They show up at the very beginning. Even though when you graph these, they look very much similar, they are in fact completely different. As you see, this has an x minus 2 on top, and this has an x minus 2 on the bottom. You have to take into account for how you start, you need to identify all the possibilities that will make the denominator 0 first. So before I want to simplify, if I choose to, let me label what makes each of these terms 0. So x minus 2, what would make that 0? 2. X plus 1, what would make that 0? Minus 1. Now, if you find that one of your terms here that made you a 0 cancels out or simplifies with the term on top, that's what shows up as a hole. So since these cancel, they create a hole. Since this minus 1 doesn't cancel, I don't have another x plus 1 on the top. This is a vertical asymptote. So holes will cancel after you're done finding the 0, and vertical asymptotes will stick around. They'll stay around.
That most from yesterday also great.
No.
Come on, ain't doing most in my heart shape, bro.
Okay.
Oh my.
So looking at the process, I have x over x times x plus 1. Before we do anything, we need to find out what makes the denominator 0. What makes that x value 0? 0. What makes x plus 1 0? Minus 1. Now I need to decide, does that simplify with anything on the top? Or as famously saying incorrectly, cancel out. This x, does it have another x value on top?
Yeah.
Yeah. So therefore, this is a
A hole.
hole. This x plus 1, do I have an x plus 1 on top?
No.
No, so this is a vertical asymptote. So holes will get canceled out. They don't quite become vertical asymptotes because they only appear at the very beginning. And then when you simplify, the rest is fine. Like so. So look in here. Let's try to find all the holes and the asymptotes. Together, they're known as what's called the points of discontinuity, a vocab term. This big old long math term right here means adding your holes with your asymptotes, which means every value down here that equals to 0 will give you a points of discontinuity. I guess they had to find out a way of collect them all together. I just didn't want to do what I did and call them assholes. So tell me, how many points of discontinuity does this rational function have?
2.
Just 2? How many values for x will make the denominator 0? Will this one have a 0? You can't plug in a value there and get 0? 0, right? 0 squared is 0. What about this one? Will this have a 0?
2.
At 2. And this one, will this have a 0?
Oh,
Minus 1. So how many points of discontinuity do I have?
3.
3. Now we need to figure out which are holes and which are asymptotes. So looking at x squared, would you say that's a hole or an asymptote?
Oh,
That's a hole, because I have another x squared that will reduce here. So that's a hole. X minus 2, would you say that's a hole or an asymptote?
oh,
That's also a hole, because I also have an x minus 2 on the top. X plus 1, would that be a hole or an asymptote?
asymptote.
That is a vertical asymptote, because I lack the x plus 1 on top. When I simplify this all out, this will stay around. This will stick around.